Good day. My name is Vasily Beskin. I am professor in Moscow Institute of Physics and Technology, and I was asked to say a few words about quantum mechanics. Quantum mechanics imply discreteness, is clear, but from the other side, all people know that quantum mechanics in wave mechanics. Let me remember from the very beginning that any wave is characterized by two values: angular frequency omega and wave vector k. We will use these values in what follows. And this is the main problem of quantum mechanics, because this is a so-called wave-particle duality, and our experience have no features of this wave-particle duality, because to understand quantum mechanics, it's necessary to shift your experience, and I would like just to discuss these points. As Richard Feynman told, I think can safely say that nobody really understands quantum mechanics. And von Neumann said that quantum mechanics is impossible to understand. Just this point about this duality. You just need to get used to it. And this statement later was formulated in a very simple way: shut up and calculate. And it's very interesting that any time when you calculate, that is, you use equation of quantum mechanics, you obtain correct result. And sometimes it's not necessary to understand the ground of this science. On the other hand, quantum mechanics is the mainstream of the modern physics. If you see how many Nobel Prizes was awarded last about 40 years, 1/3 was awarded by quantum physics. Another 1/3 from particle physics, which also some part of quantum mechanics. And the last third was awarded to astrophysics. And unfortunately, as I told, we have no quantum experience. Our experience is classical, and classical words which on the ground of two fundamental constants. One of the constant is velocity. C we know is as the speed of light, but is more general sense is velocity which takes place in the Lorentz transformation. And another constant is the gravitational constant. And our experience said that we have space, time, it's possible to discuss coordinate, event. We can discuss the trajectory, equation of motion, and within this classical site, we understand that our world is continuous. We have the principle of determinism, that is the same condition result in the same result, and possibility of long-range action, even the gravitation forces acting by the gravitational field, and observer independence, that is, there is no action of the observer of the result of observation. All these points are erroneous in quantum mechanics, and of course it's absolutely unclear to understand from our experience. And the problem was that everyday experience was up to the 18th century, that we observe matter, light, electric current. The experimental experience appearing in the beginning of the 20th century, the superconductivity, superfluidity, electronics, laser, this experimental experience was explained for everyday experience. And it was Max Planck who was the first who introduced the third fundamental constant. We will discuss it a little bit later. And in quantum world, we have no continuity. Indeed, experiment shows that Mendeleev periodic table, atomic structure of the matter, spectral analysis demonstrates that we have emission lines. We know that we have the elementary charge. It's impossible to cut the electron charge into two parts. The decreasedness of masses. Indeed, why all electrons have the same masses? This experiment demonstrates that in the quantum level, the word is discreteness. Let me stress another very important point. I will finish my talk on this very interesting thing. The scale value. Classical physics said that the scale value, there's a scale in time, in space, in principle can be made as small as desired. Quantum mechanics demonstrates that there is a fundamental problem. The scale value fundamentally cannot be made as small as desired. Another point is the principle of determinism. In quantum physics, we have probability. Indeed, if we have the radioactive atom, the quantum theory can only give the information about the probability of its decay, but it say nothing about individual atoms. The same concerns the passing of photons and electrons through the two slits. We will discuss this point a little bit later. And passing photons through the polarizer. Unfortunately, I will have no time for discussing this point. And that is the quantum world deny probabilistic language. The quantum physics have the probabilistic nature. The quantum state description to apply only to the ensemble of similarity prepared system. That is, if we have many identical particles, we have the possibility to repeat the experiment. Only in this case, quantum mechanics demonstrate reasonable result. But what to do if the object is similar? If we have only one radioactive atom, if we have only one electron passing through two slits, if we have one photon passing through the polarized region, if we have the universe, which also is singular. In this case, the quantum mechanics has some problems. And in some sense, it's necessary to change our understanding. Now it is impossible to say about the trajectory. It's necessary to say about the state and the transition probability. There is some diagram describing the colliding particles in the collider, and it's rather difficult to say what is during the interaction. And only it's possible to say what will be before the colliding, after the colliding, and describe and calculate the transition probability. Another point, unfortunately, I have no time to discuss to next position, that impossibility of long-range action. Actually, there is a correlation. If two particles, say, having total spin, which is equal to 0, move to two different galaxies, nevertheless, any particle remember that this part of two particles having total 0 spin. And the last one is observer independence. It's impossible to say about the condition of the quantum system without describing the experiment. Unfortunately, I have no time to discuss this point. And the question arises, is there anything immutable? And of course, even in quantum mechanics, there are some position which is correct in classical world as well. First of all is the conservation law. As M. Noether demonstrated, conservation of energy, momentum, and angular momentum results from independence of our experiments from time, from position, and from axis direction. This conservation remains correct in quantum mechanics. Another point concerns statistical physics, say the probability is the result of incomplete information, ergodic hypothesis, the time averaging and equivalent to the averaging of the ensemble, and the principle of active distribution of in degrees of freedom. And the quantum mechanics just originated from statistical physics, because Planck used a result obtained by Gibbs. Gibbs solved the following problems. If we have the total number of particles and they have the same full energy, how this particle will be originated in energetic levels, epsilon n. And the result is well known from statistical physics. Planck tried to understand the energetic spectrum of black body radiation. These well-known dependencies in double logarithmic scales, and you see if in this line there is a frequency, and in the upper line there is a energy density, for example. We have the power dependence. In this graph, there is a linear wave. It's possible to describe this relation from classical point of view. You see this expression doesn't contain Planck constant, but you see that there is a break in energy spectrum, and it was absolutely impossible to understand it from classical point of view. And Planck introduced the discreteness of energy levels. That is, for any frequency, harmonic oscillator, and it was the main proposal of Max Planck, that the radiating media consists of the harmonic oscillator. Harmonic oscillator, by definition, its frequency doesn't depend upon the amplitude. This implies that the energy may be arbitrary in classical physics. But Planck decided that there is the discrete number of levels, equidistant, and the distance between these levels just corresponds to quantum values. He introduced his constant h by just this proposal, that he proposed that the radiative media consists of harmonic oscillator, but their energy levels are not arbitrary, but they are equidistant. And coefficient of proportionality between the energy and frequency, we just have the dimension of energy times time, was just his constant, which he introduced for this concrete problem. And we see that if the temperature of the media is energetic dimension is much larger than the distance between levels, then the distribution of particles due to Gibbs distribution will be approximately homogeneous. It just corresponds to the power dependence in the thermal radiation. But the situation changed drastically if the energy corresponding to the temperature is much smaller than the distance between the energetic levels. In this case, you see the distribution will be absolutely different. And calculating this system, rather artificial, let me stress, he succeeded in explaining exactly the thermal radiation. It's necessary to stress that Planck told about radiating media. He told nothing about the radiation itself. The next step resulted in, again, from experiment. Experiment concerning photo effect gave following laws. That the strength of the photo current is directly proportional to the density of the light flux, but the maximum kinetic energy of electron emitted by light increases linearly with light frequency and does not depend upon its intensity. It was very, very strange. And the third law postulated that for every substance there is a red border. That is the minimum frequency of light in which the photoelectric effect is still possible. And using constant h was introduced by Planck, Einstein understood that it's possible to explain photo effect if we suppose that light is not a wave, but particles. And then he introduced the connection between the frequency and energy of photons. And then, it's a well-known expression, he could understand by very, very simple expression the physical result obtained by photo effect. And Nobel Prize was awarded by Einstein in 1921, you see, was awarded not for the general relativity. General relativity was already formulated by Einstein, but formulation of Nobel Committee is as follows: for his service to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Actually, for this expression, because it was absolutely unclear that photons, that is, the electromagnetic wave, can have the particle properties. The next step was done by Compton, who demonstrated that photon can be indeed described as a particle. That is, it has not only the energy, but momentum as well. And he demonstrated that the result of Compton effect, that is the result of interaction of photons with electrons, can be very simple explained if we suppose that the photon have not only the energy omega times h, but the momentum, vector momentum, is the wave vector, which is just the characteristic of the wave, times the same constant, which was introduced by Planck by absolutely another part of physics. Let me stress this point as well. Planck introduced this constant considering the radiating processes. And there is the interaction of particles. And Compton demonstrated that result of his experiments can be very simple explained if we write down very simple equation of energy conservation, energy and two components of momentum conservation. This is a three equation describing four values: omega, energy corresponding to energy of photons before the collision, omega prime, energy corresponding to photon after the colliding, and angle of photon motion and velocity, two component of velocity of electrons. These three equations result in one connection between the changing of wavelengths of photons and the angle of its distribution after the colliding. And you see that in this expression we see some extra combination, h divided by mass of particle, in this case mass of electrons divided by velocity of light. The dimension of these values, as one can see from the upper equation, this one, corresponds to the length, and these values, so-called Compton wavelengths, is a key characteristic of electrons. That any particles, electron in this experiment, has its own scale depending of the Planck constant. Next step, of course, it's necessary to remember Rutherford experiment. It's clear that the particles interacting with nucleus resulting from Coulomb interaction, the trajectory just corresponds to the motion of particles, and particles are particles, it's clear. But to explain the radiation, line radiation of atoms, it was necessary to change a little bit this point as well. It's well known that spectral analysis demonstrated that different atoms radiate not homogeneous radiation, but they radiate lines on definite frequency. The most simple case is the hydrogen atom, when after many experiments there was found that a very simple expression from frequency, which difference in two values when n1 and n2 are different integer numbers, and big calligraphic R here is the values, so-called Rydberg parameter, which was determined from observation. And Niels Bohr understood that it's possible to explain this expression if we use the same constant, which introduced by Planck, but use it in absolutely different way. He proposed that the angular momentum of electron in the atom also not homogeneous. It's possible for this value to have only discrete values. You see the dimension of these values, momentum times r, is just corresponds to dimension of the Planck constant, and he supposed that these values, angular momentum of electron in atom, also not homogeneous. It's possible to have only discrete values. Then, adding Coulomb interaction of electrons and proton for hydrogen atom, it's possible to determine the energy levels, these so-called terms. And what was surprising, that is possible, you see, is just the inverse square of n values was introduced in the first expression, and in this case it was possible to determine the Rydberg constant, which was determined from observations. And it's very interesting that this expression, including Planck constant, exactly reproduced the value was obtained from observations. Then it was possible to determine the characteristic scale for n is equal to unit. It corresponds to the radius of the electron orbit, is so-called Bohr radius, and as a result, it was possible to explain all lines which radiated in hydrogen atom. When we have the transition to the lower level, n is equal to 1, is the so-called Lyman series, is equal to Balmer, and so on. In Bohr atom, it's possible to calculate the undimensional values, the velocity divided that of light. You see that appearing the undimensional values, E squared divided by hc, and this values is rather small, about 1 divided by 137, is so-called fine constant, fine structure constant. But if we have not hydrogen atom, but atom with the charge Z, you see, for Z large enough, that is Z larger than 137, its velocity formally becomes more than velocity of light. And we know that there are no atoms with so large charge of the nucleus. This is one of the reasons why we have no such nucleus in the nature. Another very interesting point that if we consider very large values of parameter n, the dimension of atom becomes larger and larger. And actually, this transition was obtained in the space due to the discovery of giant molecular clouds with very, very big masses, you see, 100,000 of solar masses, and maximum values was obtained is, you see, the transition from 767 to 766. And it's very interesting that in this case, the dimension of this atom is not so small. It's some parts of millimeter in diameter. It's very interesting question why it was necessary to produce observation in space. Why it's rather difficult to observe such transition in the laboratory. I would like to explain this point a little bit later. Okay, you see that after Bohr idea that we have the discreteness is the value of angular momentum of electron in an atom, it was possible numerically explain the characteristics of atom and its radiation. But it was not clear what is the physical reason of this relation. What is the physical reason of discreteness of angular momentum? Actually, the last step was done by de Broglie with his very, very deep idea. The deepness of this idea helps in a few years to formulate main equation of quantum mechanics. And this idea was the same deepness as the idea of Maxwell, who understood that if in some cases the changing of magnetic field result in appearance of electric field is the Faraday effect. In some cases, the changing of electric field can result in the appearance of magnetic field. The same deepness was the idea of Louis de Broglie. He told that if in some case electromagnetic wave, photon, can be considered as particle, why in some case the particle, electron in the atom, can be considered as a wave? And he supposed that any particles with mass m and velocity v actually can be considered as a wave with the wavelength h divided by mv. You see, again, the same constant was introduced by Planck, appeared in this relation. And then the Bohr expression, his meaning start to be absolutely clear. If we can imagine the electron rotating around the nucleus as a wave, then the quantizing of orbit corresponds the very simple meaning. Then along the orbit there are integer number of waves. That is, the circle distance 2 pi r is equal to integer number of wavelengths of the electron. And you may check that this expression 2 pi r is equal to n lambda exactly corresponds to Bohr expression that angular momentum is n times Planck constant. And this idea help this idea that photon sometimes realized as a particle and sometimes as a wave, and the same for electrons, sometimes as a particles and sometimes as a wave. And this understanding immediately give us another very important feature of quantum mechanics. Let us which connects only from wave physics, not from quantum mechanics. This was well known from wave physics. Let us consider two waves with little bit different wave vector k. If we add these waves with the same amplitude a0, you see that there will be the characteristic scale delta x, which connects with the difference between wave vectors of these two waves. We can add different waves. The upper part corresponds to only one wave with the wave vector k. This is the wave from minus infinity to plus infinity. If we add 5 waves, you see we have another structure. If we add, in this case, 21 waves, the wave will change a lot, but in all these cases, there is a very interesting connection between the characteristic scale in k and characteristic scale in x. There is a so-called uncertainty relationship that if we have very narrow spectrum in wave vector k, as is the upper case, we have the wave propagating from minus infinity to plus infinity. But if we have finite spreading of wave vector, we immediately obtain finite spreading in x coordinate. And there is a condition between spreading in x and spreading in wave vector k. But we remember that k is connected with particle momentum. If we multiply all part of this expression to h, we obtain well-known uncertainty relationship was formulated by Heisenberg. And this relation give us very, very interesting result, which just postulate quantum mechanics. One of them is possibility of particles to move through the potential well, because if we believe that the energy of particles is smaller than the height of the potential Well, in reality, as the potential wall has some spreading L, this implies that we have also the spreading in momentum and hence in energy. So it's impossible in quantum language to think that we have exact expression of energy. In reality, we have some spreading in energy, and some part of these distributions, some energy could be larger than classical energy wall. And it gives us the possibility for quantum particles to pass through the potential wall. Interesting that the uncertainty relationship takes place not only for momentum and distance, but also for energy and time. The expression is absolutely the same, and here is possible to consider two consequences of this relation. First of all, that the width of the level is finite. That is, if the level, some energy level, have finite time, for example, due to collision with another particles, then there will be the spreading of energy. And here you see, if we have the experiment in the laboratory, when the number density of particles is large enough, the time lifetime of particle in some highest energy level is not so long. This implies that the width of this energy level not so small, and we have the overlapping of energy levels, and actually the energy levels for high values of n does not exist at all. And for laboratory experiment, you see it's possible to observe not so large values of n. But in space, when the number density is much lower than in laboratory, it was possible to observe that level I demonstrated to you. Level from when n is equal to 767. Another example is that it's impossible to measure the energy in a finite time. It's well known from people who are interested in music that it's sub-contra octave when the lowest frequency in piano, which is possible to have, it's impossible to have 1/8 of the tone, because if you calculate this expression only for appropriate frequency, you obtain that exactly this uncertainty relationship works. Okay, let's finish. My last example concerns the electron diffraction. It's just the consequence of the statement I demonstrated, that sometimes electrons, that is particle, could work as the wave. And this well-known experiment was produced in Moscow Energetic Institute in 1947 by fabricant experimental group. Later was repeated by Johnson in 1961, and the idea was as follows: to consider the passing of not electromagnetic wave, but particles, electrons, through two slits. And this experiment just demonstrated that the result quite similar to result we obtained for electromagnetic wave. And it was especially interesting because the experiment could produce the way when it was impossible to interaction between different electrons. The electrons pass through the two-slit plane step by step. There was definitely no interaction between them, but nevertheless the result was absolutely the same as for electromagnetic wave. And very interesting point is that the picture changing when someone tried to determine from what slit this electron passes. And if some experiment fixed the slit from through which this electron passed, the picture drastically changes. This is just the quantum result, and it was formulated by Feynman. Any attempt to construct a device that determines the slit through which the electron has passed, and at the same time so delicate as not to cause the violation of diffraction pattern, is doomed to failure. This indicates that electron, which our feeling is a very small object, actually passed simultaneously through these two slits. And it's possible to understand it only if we indeed decide that electron in some experiments live not as a particle but as a wave. And explanation is very simple. First of all, let us determine, is well known, determine the angular distance between characteristic features on this figure. The maximum will correspond to the case when the difference between passes from one slit and another slit just equal to wavelengths. Then for experiment for electromagnetic wave, the amplitude of electromagnetic wave will add it, and we will see the maximum on the screen. And then it's possible to determine the angle delta theta, and it's just the ratio of the, if electron have the wavelength lambda e, then there will be the scale, the ratio of lambda e divided by d. But if we try to understand from which slit electron passes, it's clear that it's necessary to have a probe, say a photon, which wavelength at any way not larger than the distance between slits, d in this figure. Then, interacting with these observing photons, the electron will take the perpendicular momentum delta p, e, and then it's possible to determine the characteristic changing of its trajectory, and you see that this changing when observing photon which collided with electron passing through the slit, the changing of angular velocity will be absolutely the same. And as Feynman formulated, when the wavelength of the observing photon is compared with the distance between the slits, its influence on the electron becomes so noticeable that the angular displacement becomes greater than the distance between the maximum of the interference and pattern. That is a very nice and physically clear understanding why it's impossible to determine the slit which corresponds to the passing of the individual electron. The electrons move as a wave passing through both slits in this experiment. And my last point is as follows. When someone add Planck constant, that is characteristic of the quantum world, to classical constant, velocity of light, and gravitational constant, these three fundamental constants are enough to combine any physical values, length, time, masses, and so on and so on. And if we draw the graph in vertical axis is the distance and the horizontal axis is the mass, there are several lines. Lines when r is proportional to masses corresponds to gravitational radius is divided the domain of classical physics and general relativity, and the domain when it's necessary to use equation of general relativity. And general relativity, let me remember, predict the existence of black holes for such scale. And another line corresponds to the Compton length. And if Compton length equates the gravitational radius, it's possible to determine characteristic mass, and it's 10⁻⁵ gram, and the characteristic length, as you see, is very, very small. And all classical physics, of course, corresponds to the distances much, much larger than these values, is so-called Planck length and Planck mass. And classical physics, you see, corresponds to the scales and masses much, much larger than these Planck values. And modern parts of physics, strings, bronze, and so on, just correspond to the scales in the vicinity of the Planck scales. And these Planck values their importance were understood by Matvey Bronstein in 30s of 20th century. His result was rediscovered 70 years ago, and actually this is a key point why there is some difficulties in constructing the quantum gravity. Matvey Bronstein demonstrated that on scales smaller than the Planck length, space-time ceases to be continuous. I stressed this point in the very beginning of my talk. And what Bronstein told, an attempt to measure a small scale delta x with a probe of mass m, according to uncertainty relation, leads to the movement of the probe, and according to general relativity, to the curvature of space. This implies that it's impossible, in principle, to have the homogeneous space-time on the scale of Planck values. I stressed this point in the beginning of my talk. And as a conclusion was formulated by Matvey Bronstein, quantum mechanics and general relativity are incompatible on small scales. And this still have some problems in understanding some features of the nature of these small scales. Nevertheless, I believe that this graph is very suitable for understanding the role of Planck values and so on. So well, thank you very much for your attention.